Answer to your names, please. Arnold. Bessie. Is here. Bishop. Greg. Here. Claudio.
Here.
Chestnut. Forward.
Here.
Erlinson. Gerard. Green. Kennedy. Leonard is here. Mohammed Boy is here. Small.
Here.
Sullivan.
Here.
And Swistak. All right, so we're going to continue our discussion of chapter 3. Let me see. Okay, so the last time we were here, I introduced to you the concept of limiting reactance, and I pointed out, or I went through a non-chemistry example and then a chemistry example. But here's one, which is another chemistry example, but it's a bit more quantitative, right? So it says here in this example, magnesium nitride can be formed by the reaction of magnesium metal with nitrogen gas. First part is asking, how many grams of magnesium nitride can be made in the reaction of 35.00 grams of magnesium and 15.00 grams of nitrogen? And then the B part is asking, how many grams of the excess reactant remains after the reaction? So again, I'm going to need some space to do this. So let me copy this here. And, okay, so this is the question. All right, so what do you think the first thing you would do in order to solve this problem? Very first thing you need to do is what? Very first thing you need to do before you do anything else.
Balanced equation.
Right, you have to figure out what the balanced equation is. Okay, so based on the information provided in the first line, what would be the reactants and what would be the products?
Magnesium and nitrogen.
Okay, so magnesium is one of the reactants, and nitrogen, which you should remember exists as what?
N2.
N2, exactly. And then the product is magnesium nitride. So the question now becomes, what's the formula for magnesium nitride? You might find a list of common ions in the tables that I've posted in the campus helpful in this regard. Magnesium nitride. One part of it. Magnesium nitride, so what's the formula? Correct. Okay. And then we need to do what? Now that we have the reactants and product formulas, what do we need to do? Balance it. So how do we balance this equation? Put 3 in front of the magnesium on this side, and that's it. You don't need to do anything else. So now we have the balance equation. So this is basically what you need to do before you do anything else, right? Okay, so the question says, how many grams of magnesium nitride? So it's asking for the mass of the product that can be made from the reaction of 35 grams of magnesium and 15 grams of nitrogen. Okay, so the way we go about this is that we start out with the 35.00 grams of magnesium And then we convert that to mole. And the way we do that is, of course, 1 mole of magnesium above, and the molar mass of magnesium, which is 24.31, if I'm not mistaken. 24.31 grams of magnesium, all right? Then we look at the mole ratio between the magnesium nitride and the magnesium, and we see it's a 1:3 mole ratio. So the way we set that up here is that we're gonna have 1 mole of Mg3N2 placed above as the numerator, and 3 moles of magnesium placed below as the denominator, and then we work that out. So we get that cheap calculator here. 35 divided by 24.31 equals that divided by 3. So according to my calculation, and please correct me if I'm wrong, but I got 0.4799 moles of Mg3N2, all right? So this would be the amount of magnesium nitride you expect to get based on this mass of magnesium. Now, we're gonna do something similar, starting with the 15.00 grams of nitrogen, all right? So like we did before, we have to convert that mass into moles. So 1 mole of nitrogen will be up top, and the molar mass of nitrogen is 14.01 times 2, which would be 28.02 grams of nitrogen. So this will go with this, and then the next mole ratio, or the next conversion factor, I should say, is the mole ratio between the nitrogen and the magnesium nitride, which would be a 1:1 mole ratio. So 1 mole of Mg3N2 would go up top, 1 mole of nitrogen will go below, so that this cancels with that, and we do the number crunching. So 15 divided by 28.02 and times 1, so that gives you, according to my calculation, 0.5353 moles of, again, Mg3N2. So now that we have these two numbers, what we do next is compare this number to this one. Since this is lower, right, that means that the magnesium is the limiting reactant. And that means that the nitrogen will be the excess reactant. Right? So it is the limiting reactant that determines how much product you expect to get. So let me continue down here. So basically, we're going to take the moles of Mg3N2, the lower one, which is 0.4799 moles of Mg3N2. And we're going to multiply that by the molar mass of magnesium nitride. So we're going to have 1 mole of Mg3N2. And up top, the molar mass of magnesium nitride, which again, because I'm too lazy, I'm going to use the molar mass calculator to do that. Mg3N2. And let's see what I get. Okay, so the answer is 100.93. So we're going to put up here 100.93 grams of Mg3N2. And then we work that out. So let's see what that gives. 0.4799 multiplied by 100.93. And according to my calculation, this works out to be equal to 48.44 grams of Mg3N2. Okay, so that's basically how we do the A part. Right? Any questions? Any questions about this, the A part? All right, so the B part is asking, maybe some more space. B part is asking how many grams of the excess reactant remain. So that's the reason why I identified the limiting reactant, right? And the excess reactant, right? The limiting reactant is the magnesium. the excess reactant is the nitrogen. So therefore, what the B part is asking is how many or how much of the excess reactant remaining, in other words, how much of the nitrogen remains. So the way we go about solving this is that we start with the limiting reactant, and based on the limiting reactant, we determine how much of the excess reactant, the nitrogen, that will react. Once we find that out, we subtract that from the original amount of nitrogen, and that will give us the amount of nitrogen remaining, right? That's basically a broad overview of what we're gonna do in the B part. So the first thing I'm gonna do is start out with the limiting reactant, which is the 35.00 grams of magnesium. And then we convert to moles like we did before. So I'm going to multiply by 1 mole of magnesium divided by the molar mass, which is 24.31 grams of magnesium. And then the next conversion factor now is where we look at the mole ratio between the magnesium and the nitrogen. And that mole ratio is 1 mole of nitrogen, which I'm going to put up here, divided by 3 moles of magnesium. All right. And then the last step in this series is where I convert the moles of nitrogen to grams of nitrogen, which is multiply that by 28.02 grams, 2 grams. So let's see what that gives. 35 divided by 24.31 divided by 3 times 28.02. Okay, so according to my calculations, the mass of the nitrogen that reacts would be 13.46. Okay, 46. So 13.45 grams of N2. N2, right? So this is the amount of nitrogen that reacted. But remember, the question is asking for the amount of nitrogen that remains. So how do we find that? We take the original mass of the nitrogen, which is 15.0 grams. So I'm going to write down here, amount of N2 remaining will be equal to the 15.00 grams of the nitrogen that reacted, and I'll subtract from that, I'm sorry, 15.00 grams of the nitrogen that was there to begin with, and I will subtract from that the 13.45 grams of nitrogen that reacted. So that works out to be 1.55 grams of nitrogen remaining. That's how you do the C part. All right. Okay, any questions about this part? C, I'm sorry, not the C part, the D part. Any questions about the D part? Any questions? Okay, so let's go to the assignment. That's the left. I think we are now able to do a couple questions. Okay, so assignment number 3. So we now can do have we done question 8? I don't remember doing it, but I could be wrong. No? All right, let's go through this quickly. Okay, so for question 8, it says balance the following equation. So how will you balance the first one? Just so how will you balance the first one? Well, you should be able to do this in no time. Should go to the pattern before. Yes, ma'am. So you're saying that this should be 2, and this should be what? 13. This is 10 and 10. Yeah, that's correct. Okay, what about the next one? 1415. Yep, that's correct. Okay, now for C, you have to figure out what the products are and then balance it, right? So let's figure out the products first. What would the products are in this case? Well,
AL2SO43
okay, that's one product. Let me write that down.
plus H.
So one of them would be AL2 and then SO what?
SO4.
SO43, okay. And the other product is H2O. Okay, very good. So now that we know what the products are, how would you go about balancing this equation? Double displacement, does that sound familiar?
Yeah.
Right, so basically what's gonna happen is that the sulfate will come together with the aluminum and the H will come together with the hydroxide to form water. Right? Okay, so balancing, how do you go about balancing this equation?
2, 3, 1, and 6.
2, 3, 1, and 6, that looks right. Yeah, that's right. Okay, very good. Then we get to D. Okay, so in case of D for number 8, actually there's only one missing reactant. Exactly, H2O. Okay, so how do we balance this? Okay, very good. All right, so I'm gonna leave you to do number 9. Clear this here. I'm gonna leave you to do number 9. In the case of number 9, what we have done is describe certain reactions in words, and you have to write down the balanced equation for them, right? If you have any problems with any of these, please feel free to call me or come by my office, all right? Let's scroll and let's see what's up. Okay. Now, this question says, it gives you the balance equation for a reaction where octane is completely combusted to form carbon dioxide and water. So the question is asking in the A part, how many moles of carbon dioxide is produced when 1.5 moles of octane reacts? So how do you think you'd approach this problem?
Check the state.
Of course. And it is balanced, so what would be the next thing you would do? Okay, start with the 1.50 moles of the octane, which is C8H18, right? Okay, now remember, you're trying to find the moles of carbon dioxide, so that means you'd have to multiply this by a certain conversion factor. What is that factor? What goes up top here as the numerator, and what goes down here as the denominator?
Carbon dioxide.
Okay, and how many moles of carbon dioxide you want to put here?
16.
16. 16 moles of CO2, and down here you're gonna put what? 2 moles of octane, C8H18, right? And that's it. And according to my calculation, this becomes 12.0 moles of CO2. All right? Okay. Any question about that? That should be fairly simple and easy to understand. Now, the next question is asking, how many grams of water are produced in this reaction? So in this case, you're gonna start off with the 1.5 moles of octane. And you're gonna try to find the grams of water. So what would be the first conversion factor you use here? What would be up here as the numerator, and what would be down here as the denominator? Okay, so 18 moles of water will go up top, right? And 2 moles of octane would be down here. Okay, so this will cancel with that. So up to this point, you get the moles of water, but remember, the question is asking for what? The grams of water or the mass of water, right? So that would mean you have to multiply this by another conversion factor, right? So what would be in this conversion factor? What would be the numerator and what would be the denominator in this case? So you said what? 18.016 is what? Oh, okay. Yeah, 18.16 grams of H2O would be the numerator. 1 mole of H2O would be below. That goes with that. So let's see what that gives. 1.5 times 18 divided by 2 times 18.016. And according to my calculations, I got 243 grams of H2O. All right. Okay. Any question about it? Any question? Let me now the C part, let me clear this. How many moles of oxygen required to form 90.0 grams of water? So we're starting with 90.0 grams of H2O, right? So what's the first thing you would do in this case? Okay, so what goes up top here, what goes below here? 1 mole will be up top. And what goes down here? Okay, 18.016 grams of H2O. So that goes with that. And then the next step will be what? Okay, so it's between water and what? Oxygen, right? So what will go down here and what will go up top? Eighteen moles of, no, wait a minute. 18 moles of H2O will go below, right? Okay, my bad. Ah. Clear this. Okay, so below, you're gonna have 80 moles of H2O, and what goes up top? 25 moles of O2. So let's see what that gives. 90 divided by 18.016 times 25 divided by 18. So according to my calculation, I got round down to 368 7.77 moles of O2. Did I do that right? Let me check it. Something doesn't look right. So this is not quite correct. Let me do it one more time, just to be sure. So this is not right. Answer should be 6.94 moles of O2. All right. Okay, any questions about this one? Any questions? Any questions? Okay, moving along, let's see if there are any other questions you can do. Oh, okay, so now we get to a limiting reactant type question. Okay, so let me clear this. Okay, so the question says, in a certain experiment, 2.5 grams of ammonia react with 2.85 grams of oxygen to produce NO2 and H2O. And there's a series of questions we ask, which reactant is limiting, how many grams of NO? Oh, that should be NO2. So please make a note of that. Arrow or typo, this should be 2 here, right? So the question is asking how many grams of NO2 are formed and how much excess reactant remains after the limiting reactant is completely consumed. So this question is very similar to the one that we did before. It's a different reaction, of course, and different numbers, but basically it's the same process, right? So let's hear what you have to say about the first step. What would be the first step in this process?
Write a balanced equation.
Okay, so very good. What would be the reactants in this equation?
NH3 and O2.
NH3 and O2, correct, okay? And what would be the products? NO2 and,
H2.
okay, very good. So now we have to
Balance.
balance it, right? So how would you go about balancing this equation? Four, 7, 4, 6 is indeed correct. Okay. So now that we have the balance equation, what will be the next step? And you can look back at the example that we did in order to help you. Okay, it's very similar, all right? So now that we have the balance equation, what will be the next step? Remember, it gives you the starting materials, the ammonia and the oxygen, all right? So what do you think the next step is? Okay, so 2.50 grams of the ammonia. But what do we do with that? Convert to mole, okay, very good. So we're gonna have 1 mole of NH3 above, and the molar mass of ammonia again, 2 bases, so. NH3, 17.03 grams, so. So 17.03 grams of ammonia, right? Okay, very good. What next? That goes with that. Okay, so what would be the next conversion factor?
You go from moles of NH to moles of NO.
Moles of NH3 to moles of NO, okay, oh no, 2. NO2, right? Okay, so how would we represent that here? In the next conversion factor, what goes up top here and what goes below here as a denominator? Four moles of, well, let's deal with the numerator first. 4 moles of what? Goes up top. NO2, and down below you're gonna have what? 4 moles of NH3, right? Okay, so we can stop there in terms of setting this up. So, where's my calculator? So let's work out this. So that's 2.5 divided by 17.03 times 1 basically. So according to my calculation, when rounded off to 368, this gives 0.147 moles of NO2, all right? Okay, next step. What's the next step? Okay, so 2.85 grams of oxygen, we convert that to. Okay, so how do we do that? What? 1 mole of O2 over what? What's the molar mass of O2? 32.00 grams of O2, right? So this goes with that, right? Next step. Six moles. Oh, no.
Or is it NO2 again?
It's NO2 again. 4 moles of NO2 up top, and what goes below? 7 moles of 2. So that this goes with that. So now we need to work this out. 2.85 divided by 32 times 4 divided by 7. So according to my calculations, this works out to 0.0509 moles. All right. So now that we have these two numbers, what do we do next?
Figure out the-
Okay, so how do we figure out the limiting reactant? Well, not just whichever one is less, whichever one's what? Based on the calculations here, whichever one does what? Produce no more or less, the lesser amount, right? So we compare these two numbers. This is less than this, which means that this here, the oxygen, would be the limiting reactant. And this would be the excess reactant, right? So it's very important that you identify the limiting reactant, right? And this is the way to go about it. After we do these series of calculations, the one that results on paper to produce the lower amount of NO2 is going to be the limiting reactant, which in this case is oxygen. Okay, so we answered this question here. What is the limiting reactant? The answer is oxygen, right? The next question is how many grams of NO2 form? So how would you go about answering that question? Well,
0.0509 moles of NO2.
all right, hold on, let me, start with this. Okay, so you're saying, I'm gonna squeeze it down here. 0.0509 grams of, I'm sorry, moles of NO2. What do you do with that?
Gonna convert it to grams.
Okay, so how do we do that? Multiply by what? What goes up top, what goes below? You're gonna convert moles to grams, what goes down here and what goes up top here?
One mole is good, one mole is.
1 mole of NO2 goes down here. And up top, you're gonna have the grams, which would be the molar mass. Me plug it in my trusty old calculator here. So, oh, wait a minute, I did something simple. Okay. Did something wrong here.
46 grams.
46.01, right, so. That goes here. 46.01 grams of NO2. So let's multiply that. We're going to multiply 0.0509 by 46.01. And according to my calculation, I'm running out to 3 sig figs, that becomes 2.34 grams of NO2. All right. Okay, any questions about this? So we have answered the second part of this question. So the remaining part is how much excess reactant remains after the limiting reactant is completely consumed. And we did, again, in the same example that we did earlier, very similar to this right here. Now, just create some space here. I'm going to erase the bottom part right here, right? So, how would you go about answering this question? how much excess reactant remains after the limited reactant is completely consumed. Based on the example that we looked at earlier. What would you start off with? Right, that's a limited reactant, right? Okay, so we start off with 2.85 grams of the ammonia. What would I do with that? I'm sorry, oxygen. My bad. Yeah, oxygen, you're right. O2. Okay, O2. So what would I do with that? Moles, right? So 1 mole, just like we did before, of O2, and down here, 32.00 grams of O2. That goes with that. What's the next step? Okay, so we're looking at a mole ratio between what and what? O2 and? No, O2 is oxygen. O2 and what? Remember, the aim is to find out how much of the ammonia remains, right? So now that we have the moles of oxygen calculated, we are going to look at the mole ratio between oxygen and what? And ammonia, exactly. So what's the mole ratio based on the balance equation? 7 moles of oxygen, which I'm going to place down here, and on top, I'm going to put 4 moles of NH3, right? Then what? Need 1 more conversion factor. And by the way, this cancels out with that, right? So we need 1 more conversion factor. So, what goes down here? 1 mole of NH3 and what goes up top? I think we calculated this earlier. Wasn't it 17.03? Or something like that? The ammonia? 17.03 grams of NH3. So this reacts, I'm sorry, this cancels out with that. So now we're going to end up with 2.85 divided by 32 times 4 divided by 7 times 17.03. And according to my calculations, this works out to be equal to 0.867 grams of ammonia. But we're not finished yet, because remember, this represents the mass of ammonia that reacted. Right? What the question is asking for is the amount of ammonia that remains. So how would we calculate that?
You subtract the reactant. Starting.
Right, so the amount of ammonia we started off with is 2.50 grams. So let me just write the amount of NH3 reactant, all right, or reactive. And as he correctly said, you take the original mass of ammonia and subtract from that the amount that we calculated to be reactive, which is 0.867 grams. And let's see what that gives. And according to my calculations, we have to round this off to 2 decimal places. So that's 1.63 grams of ammonia that not reactive, remain. That's what I should have said, remain. All right, and that's basically how that third part is done. All right. Any questions about this? Any questions? And that includes you guys out there in Zoom. Have any questions? Feel free to chip in. Any questions? All right, so let me clear this here. Let me just scroll down and see what's below it. Okay, so we can't do that yet because we haven't talked about percent yield. Okay, so let me go to the PowerPoint. So that's that. Okay, so again, this is something that you should have met before. Theoretical yield, that term basically means the amount of product that you expect to get based on your calculations, like the type of calculation that we're just looking at, right? Whatever the mass of the product or the amount of product you end up with based on those calculations, then that would be considered to be the theoretical yield. That's what you would theoretically expect to get, right? In practice, however, what you'll find more often than not is that the amount of product you would get when you do the experiment would be less than the theoretical yield, and we call that the actual yield, right? Then we use percent yield as a measure of the success of the reaction in this regard, right? Basically, that's a formula for calculating the percent yield. It is the actual yield divided by the theoretical times 100%, right? Most reactions give low yields, less than 50%. If you do a reaction and you guess and you get above 80%, you're doing pretty good, all right? Now, an interesting question being asked: why is it that in most cases the actual yield will be less than the theoretical yield? And there are a couple of reasons why. One of them would be reversible reactions, right? In other words, the product that is formed for the reaction going in one direction will itself react to get back the reactant. So the fact that some reactions are reversible is one reason why you don't get 100% yield. Another reason is the product itself can react, right? So in other words, you get a product and then some of it reacts to form other products, right? So product reaction is another reason why the percent yield is less than 100%. And then there's a third reason, and that is the fact that you can have what we call competing reactions. In other words, you might be thinking of one reaction taking place starting with the reactants, but then you have other reactions taking place starting with the same reactants. And this is particularly true for those of you who have to do organic chemistry. You're going to see where you can have this, two reactants reacting to form two potential products, right? And in organic chemistry, what they look at is, okay, how can you predict one product being formed in greater amounts compared to the other, and what can you do to favor one over the other, and so on, right? So those are the three reasons why the percent yield in most reactions will not be 100%, all right? Okay, so here's an example of a reaction between zinc and sulfur. Place them in a dish, heat it up, and you're going to get, well, theoretically, you expect to get zinc sulfide. But what will happen in this case is that not only will you get a product that you want, but you get another product. So what I said about competing reactions apply here, right? Because not only will the zinc react with sulfur, but the zinc will react with the oxygen from the atmosphere. Not only that, you might have unreacted zinc, right? And you can also have unreacted sulfur. So, for those reasons, the percent yield will not be 100%, right? And this is something that is pretty much a problem that you can't avoid. The best you can do after getting your product is purifying it to get your final product. But even then, the yield will even be less, definitely less than 100% as a result. All right. Okay. What time is it?
Quarter after.
Okay. So going back to the assignment. Okay, so number 12, we can do number 12 now. They gave you the equation and they gave you the masses of benzene and bromine, right? So the question is asking if the actual yield of the product here is, which is bromobenzene, is 56.7 grams, what is the percentage yield, all right? So the first thing I would do is what we did before, right? Calculate how much product you expect to get starting with each reactant. So let me hear what you have to say about this. Starting with 30.0 grams of C6H6. So what would you do with that? What will you put up here as the numerator and what goes down here as the denominator? 1 mole of C6H6. And down here would be the mole mass. So let me again go to the I calculated here, C686. 78.11 would be the, so I'm gonna put 78.11 grams of C686. And then the next conversion factor will be what? By the way, this will go with that, right? So the next conversion factor will be. Okay, so what goes up top here? What BR2? One mole of the bromobenzene, C6H5Br, right? And down here, you're gonna put one mole of benzene, C6H6, right? So let's see what that gives. 30 divided by 78.11, and according to my calculation, this gives 0.384 moles of C6H5Br. Okay, and then I'm going to start off with 65.0 grams of bromine, and then I'll multiply that by 1 mole of bromine divided by the molar mass of Br2, which is, again, I'm too lazy to do. Okay, 159.81. So that goes 151, I'm sorry, 0.81 grams of bromine. Make sure I'm telling you the right thing. Or 159, I'm sorry. Okay, so 159.81. So 159.81 grams of bromine. Br2. Okay, and then mole ratio this time between the bromobenzene and the bromine. And then we do that cancel that cancel that. So 65 divided by 159.81. And according to my calculation, this gives 0.407 moles of bromobenzene, C6H5Br. All right. So we compare these two. This is lower than this. So basically, this is what going to give us ultimately our theoretical yield. So I'm going to take the 0.384 moles of C6H5Br, and then I'm going to convert that to grams.
What?
So,
I'm sorry, what do you have? I can't see behind everyone's names. You have
oh,
0.47 mole of,
I'm sorry, let me get rid of that.
thank you.
Okay, so down here, I'm gonna have 1 mole of C6H5Br, and up top, the molar mass. So again, I'm going to plug the formula into my calculator here. C6H5Br, 158.02. So that goes on top here. (158.42 grams) of C6H5Br. So let's see what I get. 0.38, oops, 0.34 times 158.2. So according to my calculation, this works out to be 60.7 grams of C6H5Br. All right. So this would be the theoretical yield, right? But the actual yield is given here. So to find the percent yield, let me just erase this line up here.
Professor,
Yeah,
you have BR is 159, but then you have all of them as 158.
hold on. Oh, okay, thank you. Let's check something. C685. Oh, you know what? Hold on, C6H5ER. What's the motor mass of bromine? 79. I think this is correct, actually. So you're saying one now?
Well, I was just, the BR by itself is 159, so I.
No, the BR is 79.9.
Oh, there's two, okay.
Right. Oh, you're thinking of BR
Yeah.
two? Okay. Okay, so let me, hey, don't worry, it happens to the best of us. Where's the eraser? Let me just erase this here. Okay, so what was I doing? Oh, so now we're gonna find the percent yield, all right? So percent yield would be equal to the actual yield divided by the theoretical yield times 100%, right? So in this case, the actual yield is 56.7 grams divided by 60.7 grams, which is the theoretical yield, times 100%. So 56.7 divided by 60.7 times 100 and rounded out to 3 figs. That becomes 93.4%. And that's how that is done. All right? Any questions about this one? Any questions? Okay, so, can I hear this? Okay, let me clear this now. Let me scroll down and see what's up. Okay, I'm gonna leave number 13 for you guys to do. It's pretty much similar to what we did. The only difference is that you have to figure out what the equation is. And then balance it. And then you do a similar calculation like what we just did for the previous one. Yes, sir.
The last problem, is that percentage, is it just a percentage?
Yes, right, because it's basically, you're dividing the theoretical yield, I'm sorry, you're dividing the actual yield, which is in grams, by the theoretical yield, which is grams. The gram units will cancel out and you multiply by 100%, so the final unit would be a percent unit. Let me see, so you should be able to do number 13. Okay, yeah, number 13, that's it. All right, so in the time that we have left, let's see if we can finish up on this chapter here. So now we're gonna talk about solutions and solution stoichiometry. So I'm quite sure we're familiar with the term solution from earlier. In fact, we discussed that in chapter 2. A solution is a homogeneous mixture of two or more substances, right? Made up of two parts, you have the solutes and the solvent. So broadly speaking, the solute is a substance being dissolved, while the solvent is a substance that is doing the dissolving. Typically, if you're talking about a solution formed between a solid and a liquid, then the solid will be the solute and the liquid will be the solvent. However, if you have, let's say, two liquids, you're dissolving one in the other. Typically, the one in small amounts would be considered to be the solute, and the other liquid in larger amount would be the solvent. All right. Okay. So what we are going to look at is how do we express what we call the concentration of a solution. So when we're talking about the concentration of a solution, we're basically talking about the amount of solute present relative to either the amount of solvent or the amount of solution, right? And what you're going to see is that there are several ways of expressing the concentration of a solution, right? And that's important because, you know, it's more specific when you can quantitatively express it as opposed to say, you know, one solution is more concentrated than the other. Now, the most common way of expressing concentration is what we call molarity, right? And that's the definition of molarity that you're looking at right there. Molarity of a solution, by definition, is the moles of solute divided by the volume of the solution in liters, right? And as a result of that definition, the units of molarity can be expressed as moles per liter or uppercase M, right? So whenever you see uppercase M, when it comes to expressing the molarity of a solution, you need to understand that it's the same thing as moles per liter. Moles of solute divided by the liters of solution, all right? So for example, if you have a solution and we tell you that the solution is 0.35 M sucrose, what that tells you is that for every liter of that solution, there is 0.35 moles of sucrose present in that solution, all right? And a key thing you need to remember here is that the denominator part of that equation specifically says liters of solution, not liters of solvent, right? And that's also very important to keep in mind when you're making up solutions, right? In fact, for the lab that you guys are going to do later on, you're going to see how this comes into play, all right? So, so how do we prepare a solution of a specific molarity? Well, the main piece of glassware, and this is assuming that you're starting from scratch. In other words, you're starting from your solute and you're going to make up the solution. For example, if the solvent is water, you're going to add water to it to make up the solution. You have to be careful in terms of doing your calculations in order to determine how much solute you're going to use. And you have to know also what volume of solution that you're trying to make. Now, based on what I see here in this picture, they're making a 0.01000 M solution of potassium permanganate, right? So what that means is that for every 1 liter of the solution, the number of moles would be 0.01000 moles, right? Now, of course, there's no way of measuring directly the moles, right? What you'd have to do is determine the equivalent amount in grams, right? So you have to calculate that, right? Which means that you have to determine the molar mass of this compound, and then you multiply the molar mass by the moles given, and that gives you the grams. So once you determine the grams, right, then you're going to weigh it, right? And that's what this person did. So it turns out that the calculation results in the fact that 0.01000 moles is equal to 1.580 grams, right? And then you're going to place, now, let me just say, this person, I wouldn't go about doing it the way this person is doing it, right? But basically, what this person did is that they put some water in the flask. This is called, by the way, a volumetric flask. You're going to be introduced to it in the lab later on, right? Volumetric flasks, these are flasks which are designed to measure one specific volume, right? So you can have a flask which measures, I think the smallest one I've seen is 10 mils, or 25 mils, or 50 mils, and so on, right? That one is a 1 liter flask, 1000 mils, right? So, and they're very accurately made. In fact, if I'm not mistaken, they're made such that it records the volume to 2 decimal places when expressed in mil, right? And for that reason, and this is for future reference, if you, you know, in your future careers, if you work in labs, whenever you are finished with these flasks and you have to clean them and wash them, please do not put them in the oven to dry, right? Because what will happen is, as we all know, glassware, like most other substances, when heated will expand, and when cool will contract. And there's no guarantee that it will contract back to the same volume that you started off with, and therefore you'd have ruined it because, as I said before, it's accurately made, right? So what I would do if I were to make this solution is that I wouldn't start off with water in the flask first. I would add the solid to the flask, right? And then I would add water to about halfway, right? And then I'll stop it, shake it up to make sure the solution is homogeneous, and then I'll add more water until the meniscus gets to a mark. Now, and again, you're going to see it in the flask that you were working with in the lab. There's a mark which you can't see here, but there's a mark that is etched on the stem of the flask, which basically shows you where the 1 liter level is, right? So basically, I would start off by adding the solid to it, add water to about half or maybe a third way, stopper it, shake it up to make sure that the solution is homogeneous, and then add water to it until the bottom of the meniscus gets to that mark. Stopper it again, shake it up, make sure it's homogeneous, and that's it. And that's how you prepare the solution, right? And so that's what this person did well. Like I said, I wouldn't do it this way. But I would do this step here, where I'll just add water using like a pipette or something, drop by drop, just to make sure that the meniscus gets to the mark, and then that would be it. And that's how you make the solution, all right? And this is basically standard practice in labs all over. It doesn't matter if it's a teaching lab like ours or a research lab. Basically, when an experiment calls for a solution of a specific polarity, this is what you have to do in order to make up such solutions. Okay, let's see here. All right, let's see how many of these questions we can do before last. All right, so the first question is, what is the molarity of a solution in which 333 grams of potassium, let me copy this here. We copy all these here. So the first question is, what is the molarity of a solution? And it gives you the mass of the solute and the volume of the solution, 10.0 liters. So remember, the definition of molarity is moles of solute divided by liters of solution. All right? So, based on that definition, how would you tackle this problem? The question is asking for the molarity. Right? It gives you the mass of the solute, which is potassium hydrogen carbonate, and it gives you the volume of the solution. Right? So I would say they gave you the volume of the solution already. I put 10.0 liters down here, right? Oops, 10.0 liters, all right? So that's the volume of the solution. How would you get the moles of the solute? Times. What would you multiply this by? 1 mole over what goes down here? Yeah, but specifically what? Remember, it's potassium hydrogen carbonate. What I would do, if I were you, is figure out what the formula of potassium hydrogen carbonate is, right? So what's the formula for potassium hydrogen carbonate?
HCH.
No, well, K is one of it. K what? KH
CO3.
CO3, exactly. So you need to find the molar mass of KHCO3. So let me go to my calculator again. Okay, so KHCO3. And oops, I did something wrong again. Okay. This should be 3. So let's see, 100.12, right? So down here, I'm gonna put 100.12 grams, right? And that's it, because the gram units will cancel out here and here, and your final unit will be moles per liter, which will be the same thing as M. So let's do the number crunching. 333 divided by 100.12, and then divide that by 10. So the answer I got, when rounded up to 3 sig figs, will be 0.333 M, or 0.33 3 moles per liter. Alright? And that's how that is done. So that's relatively easy, alright? Any question about this one? Any questions? Questions? Okay, let's see here. The next example is, oh, okay. They gave you the molarity, right? This is the molarity right here, 6.68 M, right? Of sodium hydroxide. And in the A part, they're asking how many moles of sodium hydroxide are required to prepare 0.500 liters of a 6.68 M sodium hydroxide solution. So how would you go about doing that? Let me remind you again that molarity is equal to moles of solute divided by liters of solution. All right, so how would you solve this problem? They gave you the volume in liters, and they gave you the molarity, which is 6.68 M. Exactly, you multiply the molarity, so to get the moles of solute, that will be equal to the molarity times liters of solution, right? Which you're given both of these, because the molarity is 6.68 moles per liter multiplied by 0.500 liters. And according to my calculation, oh, that's 3.34. One of the few calculations I can include in my head. Moles. That's how you do that. All right. Any questions about this one? Any questions? Okay. So let's move on now to the B part. Go down here. Here's the space here. Okay, so the B part is asking, oh, yeah, the question?
What do you have under the 6.68 moles?
Per liter, that should be L. That's L. So this L cancels out with that liter unit, right? Okay, B. How many liters of 6.68 M sodium hydroxide can we prepare with 2.35 kilograms of sodium hydroxide? So they gave you the mass of sodium hydroxide, they gave you the molarity, and the question is asking for the liters. So how do you get the liters? We can go to this way of expressing that relationship, right? So to get the liters of solution, what would that be equal to? Huh? Look at this equation right here. Mole is equal to molarity times liters, right? So if you want to rearrange it to get the liters, that would be what? Moles of solute divided by molarity, all right? So how do we get the moles? Hint, hint. How do we get moles? Okay, so 2.35 kilograms convert to grams. How do you convert to grams? What goes up here, what goes down here? 1,000 grams above, 1 kilogram below. Okay, so that goes with that. And then what's the next conversion factor? Remember, we're trying to get the moles, right? Okay, so what goes up here?
1 mole.
1 mole of sodium hydroxide, and down here would be the molar mass. If I remember correctly, the molar mass of sodium hydroxide is 40.00 grams, right? Okay, so that takes care of the numerator part. And then we divide all of that by the denominator, which would be the molarity, which is 6.68 moles per liter, right? So the moles will cancel out here and here. So the only unit remaining after all the other units are canceled out will be the liter unit. So all we have to do now is the numbers. 2.35 times 1,000. 2.35 times 1,000 equals that divided by 40, divided by 6.68, And according to my calculations, I got, when rounded off the three sig figs, 8.79 liters. So that's how that is done. Any questions? Yes, sir. Any problems in the? Yeah, actually,
Say it's 14.
let me see here,
Yeah.
yeah, questions like, yeah, what he said, 14, 15, 16, 17, 18, yeah, all those questions, basically, deal with what we just did. All right, okay, I'm gonna stop here. I want you to, on your own, to try the last question, right? And we can come together, next class and we can discuss it. If you have any problems, I can help you, right? Just remind you about the event tomorrow, if you can make it, please do. Concerning, you know what, I've decided, should I give extra credit?
Absolutely.
Okay, I'm gonna decide and post online what exactly what extra credit is if you attend, right? I think I've provided a Zoom link just in case you can't make it in person. So. That's fine. So it's tomorrow at 12:30. Unfortunately, for those of you who can't make it in person, you won't benefit from the pizza that will be available. That's too bad. All right. All right, so that's it. You guys over here in Zoom, I'll be signing off right now.